All right, hello. So, I know you emailed me about the videos. Okay, so the problems, I think I'll just get started on each of them and just kind of go over my thought process on what I think is the, not optimal, because obviously, there's always going to be a better solution than, the ones I'm going to give it to you, but, a pretty reasonable solution and my reasonable attempt to them. So these are pretty hard problems, I'm not gonna lie. All of them, not just the ones you told me, but pretty much all of them. So yeah, if you try, I know you might be oh well, where do you make this logical leap? If it acts as any reassurance, you'll get there. If you what I mean, you'll probably be doing a math team in high school. From what I've seen, you seem pretty interested in it. The big thing is, it's going to be to that point where, you might be oh, well, how do you know when to make those intuitive jumps? But the nice thing about it is that it's kind of just practice, right? You just got to keep doing practice, and you'll see stuff like this over and over again, and you'll start knowing. A good example of that is the problem 3, the one you sent me. So let's first start on what we're looking on here, right? First of all, it's a system of equations, but not in an ordinary sense, because in middle school, you might be used to doing system of equations with just normal, for example, y equals mx plus b, right? Stuff like that. But here you're given a bit of stuff that's a bit different. Now, for the first problem, or for the first equation, it's kind of nice because you don't have another equation, so you can literally just solve for it by itself and have it work out. So, before I even get into this, you've probably not seen something like this before, which is why the question might seem intimidating, but I'm going to show you this, right? Think of a fraction with the denominator 1 and the numerator 1 more than the denominator. That's just going to be 2, right? That's equal to 2. Now, what happens if I give you a denominator of 100, but the numerator is 101? That's still 1 more than the denominator, but that's a lot closer to 1. That's a 1.01. Now, say if I give you 1 million and 1, right, over 1 million, that's really, really close to 1. Now, why am I even bringing this up? It's because the idea of infinity, right? Here, there's an infinite amount of root x's, and that's important because you gotta understand. I could just show you the trick, but if you don't understand the trick, there's no point on doing the trick, right? So my point is to kind of build the reasoning on why this trick works. But basically, it's the idea, when you take calculus, you'll definitely run into this. It's the idea that as you approach infinity, the numerator, or in this case not the numerator, but as you approach infinity, if you have 1 less than something, those two are pretty much the exact same. If you had an infinity plus 1 over infinity, okay, that's a really bad way of writing it, and you'll learn why later on, but this is terrible notation. But regardless, for purposes, this is still equal to 1. Because the 1 is so insignificant, it just doesn't matter. So now why do I bring that up? Because you can use that same idea on reasoning that, hey, 4 is equal to square root of x plus this whole thing is literally just equal to the thing on the outside, right? Meaning that this root x is just equal to the thing on the outside, which is equal to 4. So kind of take some time on figuring out why that jump makes sense. But it's nice to know because now x is by itself in a really simple equation. Just square both sides, you get 16 is equal to x plus 4, so x is equal to 12. Now, the second equation is really straightforward. I'm not going to explain the math behind it because it's literally just plugging in numbers and doing arithmetic. So y is just equal to 12 cubed plus 3 times 12 squared minus 3 times 12 plus 1. Now, I could do the arithmetic, but I don't want this video being long for no reason. So if anything, I'm just going to do it on my calculator. Why am I doing it on my calculator? Because the whole point of these videos is literally to explain the thought process, not the actual arithmetic. So y is equal to 2125. Then x times y is equal to 25,500. So the quotient is 25, and the remainder is 500. So 500 plus 25 is equal to 525. All right. So yeah, it's pretty much that whole problem hinges on that one trick. Problem 4, I'm not gonna lie, it was kind of hard to understand. When I first read it, I was like, okay, what the heck? Now, it's here where I'm gonna explain a really important thing called context, right? You know what context is. But in terms of problems, what does context mean in math competitions? Well, think of it this way. I'm a junior in math team, right? I've learned a lot of things in math team. I've learned a lot of tricks, and especially when stuff with 3D planes, I've learned a lot of tricks that can help me in problems with 3D planes. However, this problem is meant for an 8th grader. An 8th grader probably does not have the same theorems that I know and stuff like that. And that's okay. But the whole point of me underlying that is because it kind of solves the notion that you don't need fancy stuff to solve this problem. And why do I say that? It's because the average person solving this problem, the average 8th grader, is definitely going to think, oh, there's probably some theorem that I could use that's really helpful in 3D planes. But no, this problem was designed for 8th grader, and sure, the logical leaps might be hard, but the actual theorems that you need to know as an 8th grader should be relatively straightforward. So now, let's actually get to the problem. So with these, what does it mean for two equations to be tangent? That just means meets once, or in other cases just has a solution. So that means that these two are equal, so x squared plus y squared plus z squared is equal to 1 over x squared plus 1 over y squared plus 1 over z squared. Now you're going to be like, okay, well, how do I solve this? But there's a really nice hint. The hint is real integral value. This is important because integral just means integer. So both of these have to be an integer, and for it to be an integer, you have to plug in an integer, meaning that x, y, and z, the pair, has to just be all integers. Now, what can I do? Well, first of all, you could plug stuff in. What happens if you plug in 0? Well, the right-hand side doesn't work because you have 1 over zeros. But if you plug in 1, which is probably going to be your next intuitive leap, it'll work out because both sides equal 3. And this is a distinct value, m. So m is equal to 3, and that's important because there's no other value. So now we got first half of the problem. Why did I plug in 1? It's just brute forcing at that point. It's a strategy that I know sounds kind of lazy, but it's probably what the problem writer wanted you to do. If you really want to consider it, think of it in parts. For what does x equal 1 over x squared? There's only one real solution. There's two real solutions, but I'm going to get that in a second. It's 1 and negative 1, but yeah, that 1, right? So it adds up to 3. So now we have one pair where it's 1, 1, 1. But what happens if I changed one of these to negative 1? Does anything change? Think of that. No, it doesn't change because negative 1 squared is the same as 1 squared, right? But they're both 1. So that means that if I change any of these to negative 1, it doesn't matter. So I could have 1, 1, 1. I could have negative 1, 1, negative 1. I could have negative 1, negative 1, negative 1, right? It doesn't matter. So I could list off pairing these, but let's do a smarter way of counting them. How many choices do I have for the first one? I have 2. It's either negative 1 or 1. How many choices do I have for the second one? Also 2. And how many choices for the last one? It's also 2, right? So I have 2 choices for the first one, 2 choices for the middle one, and 2 choices for the last one. What is that? That's just 2 times 2 times 2, which is 8. So therefore, n is just equal to 8. Now, the problem has you finding this. I'm not going to do that on paper because, like I said, the whole point is this solution. There's the strategies, not the actual arithmetic. So doing that on my calculator, quotient. So you should get this whole thing equals 7073, which just equals to 884 as a quotient. So that's your answer. All right. Yeah, it was pretty interesting seeing how people went about these problems. I don't think anybody got it right, but it's still because wait, actually, you didn't ask for 5. You asked for 6. All right. Okay. This one took concepts that are somewhat arbitrarily basic, but at the same time a more advanced application of it. So what do I mean by that? Well, let's just get started, right? Now, parabola, right? So you might be okay. Actually, no. I'm just gonna go into the problem. I'm not gonna get ahead of myself. But a projectile's trajectory can be modeled as that parabola. First thing in my head, parabola, right? What is a parabola looking like? That's what I'm thinking. It's a negative coefficient, so the start is downward facing. So that's probably what my object looked like. Does it need scale? No, it's just a shape, right? Now, note, t is the time. V, well, what is this? What is V little circle? Or, well, it looks like a 0. This means V sub 0, or other people say V naught. For purposes of this, anytime there's a little zero, I'm going to say not, because that's like the way you say it. And if you're confused about why like stuff like that exists, you're like, if you're thinking that, oh, does it mean like v times 0? It's just the variable. Like, the reason you have v naught and like is because in physics, when you take a physics course in sophomore or junior year, depends on when you want to take it. Like, you'll for sure have this by junior year, but the reason you have stuff like v naught is because you'll want to, like, you'll have a variable of velocity, but there's going to be velocities in multiple different times. There's v naught for your initial velocity. There's vf for your final velocity. There's your vi, which is sometimes initial velocity, or in other words, it's v at your ith position. But yeah, that's what the like subscript means. It's not anything fancy. So if you're confused about that, just don't worry too much about it. But yapping aside, we can just move on to the next part, which is he fires a catapult or a cannonball, and the initial velocity is that. So boom, we already have a coefficient. You have negative 16t squared plus 40t plus, do we have h naught? We don't. We do have the maximum height, but we don't. We have an interval of the maximum height, but we don't have h naught. So now, how do I find, like, well we need height, right? How do I find the max height? Well, what's the vertex of the parabola? That's your max height. In other words, like, if I want to find the vertex of the parabola, how do I do that? There's just a really useful formula for that, which is the x is equal to negative b over 2a. And you plug that x into the equation. So negative b over 2a is negative 40 over negative 32, which is just 5 over 4. Plugging that into this gives you your max height. So negative 16 times 5 over 4 squared plus 40 times 5 over 4 plus h naught is equal to h max. I'm kind of running out of space on the screen, but yeah, h max, right? I'm gonna... Alright, now what? I'm just going to simplify stuff. The 16 cancels out with the 4 squared on the bottom, so you have negative 25. The 40 cancels out with the 4, so you have 50, plus h naught is equal to h. I'm just going to leave it as h now, because we know it's h max. So, h is just equal to h naught plus 25. What does this mean? The max height is just equal to 25 more than your initial height. Well, we don't know what the max height, or we want to solve for initial height. We don't know what the max height is, but we know an interval. We know that it lies in an interval of 32, 67, which, if you remember interval notation, just means that h is less than or equal to 67, but is greater than or equal to 32. Plugging in that gives us 32 is less than or equal to h naught plus 25, is less than or equal to 67. Subtracting 25 on each side gives us 7 is less than h naught is, or 7 is greater than, or yeah, 7 is less than h naught, and h naught is less than 42. So now the final thing is, so yeah, that's your interval. So h naught lies in the interval of 7, 42. And you want to find m times n. So 42, so this is m, this is n. 42 times 7, that's just 294. Sorry. Alright, so what do we do here? What we did, we basically had we broke it up into steps. Notice how every problem I've done so far doesn't, like, basically have me tackling the whole thing. It's basically me breaking it into manageable steps, which is probably something you've not encountered in middle school math team. A lot of the times those problems are really straightforward, so you know where to go. But here, I'm like, I can't do that, because it's a very unreasonable strategy, because each problem is its like own little conquest you have to solve. So because of that, I'm going to break it up into problems. So I'm going to be like, okay, first of all, I got my quadratic. Now what? I got to find the max like value of that quadratic, which we can use our like tools that we already know in the past. Now that we have that, we gotta, like, we basically instantiate a relationship between h and h naught, and using that, we get the final piece of information, which finally allows us to solve for h naught. So as long as you break things up into parts, it's very manageable. You'll find it's actually more manageable than you think it would initially be. Okay. So Alright, what is the next problem you wanted? I think it was 12. Alright, 12 was a doozy. It's a lot of geometry. Actually, I find, like, yeah, these three last problems were all geometry. But, yeah, it's kind of, like, more... You have to be, like, a really good geometry person to figure this out, which it's okay if you weren't, because, like, you're also taking geometry right now. But enough of that thing aside. So, first of all, the first thing I'm going to do, right, I'm going to draw a diagram. I don't know what it looks like because it's going to be scary, so I'm going to draw a diagram. That's, like, a good strategy. So, I'm going to draw, like, a little circle. Now, I'm going to draw more circles, right? Basically, what it means, I'll draw the diagram for you. It's going to look like something like this, right? Where each of the thing is tangent to the other circle and then the walls. So it looks like this, and you should pretty much figure out what the problem looks like, but if not, I'm just going to flash a picture on the thing. I'll be back. Okay, so it kind of looks something like this, if that helps. I guess that might help you. So now I'm going to make another step, and this is a strategy that it's used a lot of diamond geometry problems, but you have a side length of 15. I'm going to hold off on that. I'm going to be like, wait a second, I don't want to do 15 yet. Why? Because I need to figure out something, which is I need to figure out, like, ratios, right? Why do I need to figure out ratios? Because you don't know, like, it's an infinite amount of circles. So the strategy that I like to do is think about it like areas, right? What am I solving for? I'm trying to solve for this big circle, so I'm just going to call this B for big. And then this infinite sum. Now I'm going to use some fancy high school like terminology, but the sum, it's just a symbol, right? Don't be scared. We're not going to do any like any calculus things or anything like that. Literally just the sum of this means sum, right? It's like a fancy way of just saying sum of like infinite, right? So I'm going to it's just going to be the sum of all the little circles times 3 plus the B for the big circle. So that's what our final thing is going to look like. So I'm actually just going to keep this right up here, just so we have this as a little template. So now, before we do that, I'm going to go ahead and set like the side length equal to 1. Why am I doing this? Because it's a strategy. It's called like without loss of generality. Yeah, without loss of generality, I set it equal to 1 because it helps me like cancel stuff out. Because with ratios, you don't want this 15 because that 15 will be annoying. The 1 makes all the ratios really easy. Think of it this way, right? If I have a box and I have a square, if this side length, if I have a circle inside that box, if this side length was like 72 and I wanted to figure out the proportion of the circle covering the square, it would be really annoying with the 72. But it's also the same proportion if I just let this equal to 1. So that's like a trick. So now, the reason I do this is because I need to do a lot of figuring out side lengths. So now, I'm going to set it equal to 1, and I'm going to use a red pen. So, first of all, I'm going to draw a radius, right? I'm going to draw a radius here. And I'm also just going to connect this, right? This just makes a little triangle. Now this triangle is nice because I can figure out like side lengths pretty easily. So this is just 1 over 2 because this is the midpoint. Now using your 30, 60, 90 triangles, I'm going to assume that you're pretty comfortable with those. So I'm going to say that this is just 1 over 2 root 3, right? If you don't understand where I got that, just think of a 30, 60, 90 triangle. And I'm also going to try going pretty slowly because I know this is going to take a while, but I'm trying to go really slowly because it's going to be a hard problem. So yeah, so this is equal to 1 over 2 root 3. That's equal to radius. Okay, we found B. Like B is just equal to pi times 1 over 2 root 3 squared, right? Obviously there's the 15, but we'll like handle that in a second because I'll show you why I'm doing, like, everything's just going to come together at the end, I promise. Okay, now this is the hard part. Now I need to find out what is the radius of this smaller circle. Well, I'm going to make another altitude. I'm going to call this x. I'm also going to call this x. I'm going to call this one x as well. But actually no, I'm just going to call these two x's, right? And then this is just 1 over 2 root 3, if you remember. So I don't know what this length is. So how can I represent it in terms of x and things that we already know? Well, this whole hypotenuse is just equal to 1 over root 3. Why is that? Because 30, 60, 90 triangle is just times 2. And we have 1 over root 3, but we're also subtracting 1 over 2 root 3 and then x, right? That's equal to this length over here. So that's equal to, you can turn this into 2 and turn this into 2. That'll just be equal to 1 over 2 root 3 minus x. Now, why did I do that? Because we want to solve for x. And we can do that because we have a ratio now. We know the side length of this, we know the side length of this, and we know that the ratio of them is 2, right? So the top one, 1 over 2 root 3 minus x over x is equal to 2. And now we can solve for x. This is huge. And I'll show you why it's huge in a second. Because 2x is equal to 1 over 2 root 3 minus x. So 3x is equal to 1 over 2 root 3. So x is equal to 1 over 6 root 3. Now, why is that huge? If we know, so think of it this way, right? We're like finding the relationships between two circles next to each other. So we're finding the relationship between this circle and this circle. And I'm going to argue that since you're scaling down the radius, that relationship is going to hold true for this circle and this circle. So if we find the relationship between two existing circles, we can just use that and kind of make a lot of general statements based off that. So that's pretty much why I'm doing what I'm doing. Now back to the problem. We have 1 over 6 root 3 as our new radius. But our old radius, which was this, that's just equal to 1 over 2 root 3. Now do you notice something between these two ones? Like, I'll give you a second, but moving on. This smaller circle is just 1/3 the radius. So now, why is that important? Because I basically have taken all this math and used it to prove something. Like, I know you've done a lot of proofs in geometry, but this is kind of like proofs in like math competition. Like, obviously it's not going to be like your 2-column proofs that you do from that, but like now that we have that the radius is 1 over 3 of the previous circle radius, it helps because now you're like, okay, now every circle is just going to be 1/3 of the radius of the circle before it. Now what does that mean? Think of it this for a second, right? Have you ever heard of like this? I know the first time I heard of this was not actually in a math class. It was actually in a game theory. Yeah, if you've heard of the YouTube channel Game Theory, this is where I heard of it. It was film theory, trying to figure out like how much money Scrooge McDuck had, something like that. But it's like called the square cube law, where if two side lengths have a proportionality of like 1 over 1 over k, or like actually better yet, one side length is k times the other one, the areas are going to be k squared of each other, right? So say I have like a box or a square and a square. This one has side lengths 2, or this one, the first one has a side length of 1, the second one has double that. The area is just going to be 2 squared. So the areas are going to be, this area is going to be 4 times this one, right? So now that helps because this one, like the fact that one radius is 1/3 of the next one shows that the next circle has an area that is 1/9 the area of the circle between it, right? So we did all that math to prove this huge statement. So now, doing that, we can get back to our problem. Now this is where the math starts. Alright, so I don't know what I want. Okay, I'm actually just going to make a copy of this. Duplicate it. Did it work? No, it didn't. Oh, I have to click paste. Right? Doing that? Okay, I don't know. But, okay. I guess I just won't have a diagram. Alright. So, back to our original circle. Or, actually, no, I really want a diagram. Okay. Give me 1 second. Okay. Now, we have this, right? Now, let's go back to the 15. Well, what's this bigger triangle? The big radius, that's just, the big radius is just equal to 15 over 2 times, or 15 over 2 root 3. I'll let you prove that one on your own, because you can, if you've gone this far in the problem, you can definitely prove that on yourself. So that's the big radius. Now the next circle is going to be a ninth of that. So I'm going to let that equal to A. I'll show you why in a second. But that's just going to be 15, or wait, how do I? Yeah, I want to handle both areas. Okay. So yeah, the area of B is just going to be equal to 15 over 2 root 3 squared pi. Now, what is the smaller circle? That's just 1/9 of 15 over 2 root 3 squared times pi, right? Now, this is kind of like the final step in the process, but this is using infinite geometric series, right? Basically, if you have, like, you've probably covered geometric series in algebra. What is a geometric series? It's something like 1, 3, 9, like where you're multiplying by a number to get to the next number. If you have an infinite amount of those and you want the sum of them, it's just going to be the first term, A, over 1 minus the ratio. So, like, now that we have the first term, because remember how we said we're starting at the next circle? We have that circle of A, which is 1/9 of 15 over 2 root 3 squared pi. That's your first term, over 1 minus the ratio between each circle, which is 8 over 9. And then there's 3 of those. So I know we did a lot of math in that one step, but basically this is just corresponding to that. And yeah, so then there's 3 of those, and then we're adding our original circle. I'm just going to leave that as B just because I kind of don't want to see all this math on the screen. But yeah, a lot of math, but yeah, this is a hard problem too, so I'm giving it its duty for doing a lot of problem. Okay, so also I realized I wrote 8 over 9. I meant 1 over 9. So yeah, so where do we start? Well, first let's simplify the top. 15 squared over 2 root 3. Well, what is 2 root 3? That's just root 12. So over 12 times 9 pi over, and then 3 times that, over 8 over 9. I know we just did a lot of math, but yeah, like, just kind of bear with me for these next couple of steps. But something you'll notice, these 9s will cancel, which is pretty cool. And we'll have 3 times 15 squared over 12 times 8 pi. And now can we cancel a couple things? Yeah, this turns into 4, this turns into 1. And then 3 times, yeah, and then so you'll just be left with 225 pi over 32. And now we have to add the big circle, which is just, yeah, I'm just going to copy and paste this, or just drag it down here. Because the problem with doing a whiteboard is that not everything's on the screen at the same time, so it's kind of annoying. But yeah, now we have all of that. So now this is just 225 over 12 pi, 225 pi. Okay. Now I just add them. So now, wait, what is the problem asking for? Okay, m over n pi. Okay, so I think that you're pretty much going to be able to combine fractions by yourself, right? I don't want to really get into the nitty gritty of this. It's pretty easy, just common denominators. You can basically, how would you look for common denominators? Yeah, I don't know. You probably like multiply each one by, you multiply the first one by 3, and then whatever that gets you to get to 12. But I'm just going to add them on my calculator just to give you the final answer. So that is just equal to 825 over 32 pi. And that will be 825 plus 32. That is just 857. That's just going to be your final answer. I know we kind of cheated on the last step, but like I don't like want to like really hold you accountable for doing all this math, and like if you're this far and you're not in a competition, like you kind of don't even want to like, you know how to combine 2 fractions, right? So just kind of get into like the habit of like, yeah, if you know that there's an end step, it's okay to use your calculator. Obviously don't depend on it because arithmetic is good to practice. But yeah, it was a long problem, so I think doing the calculator to combine the last two steps is pretty rightful. But yeah, before I move on to the next problem, I'm just going to explain what the heck I just did. Because I know you probably did get lost at some point, which is okay. Because I know I probably would have gotten lost if I saw this much math as an 8th grader. But what you did, you identified that, hey, first of all, you need to do an infinite series, right? It's going to be this big circle plus 3 times whatever series those are, right? So then after that, we needed to figure out, well, what is the common ratio? All this red math was done just so you can find the common ratio. And it's nice because finding that common ratio, like there's different ways to like go about it. I showed like a really analytical way of going about it where you're like really trying to like just get number crunching it, because if you think about it, at the heart of every proof is just more algebra, right? So using that, you figure out that, okay, the ratio is 1/9, and then by that, like the cookie crumbles, right? You pretty much have everything that you need. So n is just, or not n, or the common ratio r is just going to be 1/9, and then that just leads you to do all this math, gives you 857. So yeah, if you have any questions, please ask me. Like, I know it's kind of confusing doing these problems, but please do ask me the solutions to these. So yeah, all right. And this is where I got the problem too. If you want, I can email you the solution. Like the proof, it's similar to what they had on here, but like it's a pretty straightforward proof. This is where I got the diagram, if you're curious. And if you also want to read more about it, they cover a really, like, this is kind of straightforward way of doing the proof. Like, I don't know how you can do it otherwise. So yeah, it's like pretty much the same thing. They just use more like fancy vocab. So yeah, okay. Yeah. All right. Problem 13. I think problem 13 is a lot easier than problem 12. So let's get started. All right. Okay, so there's a clock, unlike other clocks. Okay, so when I talked to Colleen about this, I was low-key like, bro, like you kind of said it in like a debatable way. But what he means by tangent, if you're still confused after this point, it's fine. But what he means by tangent is literally like the clock hands are like this, like the clock fully extends and touches the circumference of the circle. That's what he means. So that's kind of what it was saying, but that's obviously like that's not gonna, like, knowing that won't solve the problem for you. So let's move on and let's get to the solution. So first of all, I'm gonna draw a clock at 12 o'clock, right? Now let's think of it this way, right? First of all, when one of the areas is twice of the other areas, just think intuitively what that means. What is it gonna look like? If you think about it, right, you can use algebra to prove it. Like, be like x plus x over 2 is equal to 1, where 1 is the full thing of the triangle. You'll see that x is equal to 2 over 3, meaning that one of these, it's going to look like this, right? It's not going to look like this, because notice how both sides are equal. You might be like, oh, it's a half, but both sides are equal. You want one side to be, or one segment to be twice as much as the other. So this is 2 over 3, this is 1 over 3. One is twice the other, right? So that's the underlying, like, thing. Now, that's half the problem. But it's an important part of half the problem, because I'm going to ask you another follow-up question. How much minutes ahead will it be? Think of it. It's going to be 60 over 3 minutes ahead. So 20 minutes ahead, right? So one of these arms is going to be 20, or one of these hands is going to be 20 minutes past the other. Now, that's an important number. I'm going to write 20 and box it up in this top corner. All right. Now, I'm going to do case 1. Case 1 is first time after midnight. So these clocks move at different rates, but they cover a different amount of distance, but they cover the same time. Now notice I said 3 variables. I said distance, rate, and time. You should be thinking of a formula now. It's our favorite, d is equal to RT. Distance equals rate times time. Now, how can we use it in this place? Well, you're not going a distance, right? But you are, technically you are going a distance, actually. You're going the arc length of the circle. Not in your traditional, I'm writing a mile distance, but it's still a distance nevertheless. So now that you get to this point, okay, well, you have the equals RT. Now you just have to do system of equations and think about it, right? So you have d equals rt, and for the first one, I'm going to say distance 1 is the hour hand and distance 2 is the minute hand. So d2 minus d1, well, what am I saying? I'm saying how much more is d2 or past d1? That's just equal to 20, right? Because one hand has to be 20 past the other hand. All right, that's promising. Now let's use d equals rt on our separate equations, right? Because d2, that's just equal to the rate, which is, let's just say, one like segment per minute. If you think of that, like if you, there's a lot of different units you can use for this problem. I think that the easiest one is like minute, like arc degree per like minute. I don't know, but basically, you just need to identify a ratio. It's not really what the numbers mean. It's more the ratio that you get. So this one just moves at like 1 because it travels 1 minute per like minute. So that's just equal to 1 times t. So d2 is just equal to t. What does that mean? Plug in a time in minutes. That's what position the minute hand will be. And that makes sense intuitively, right? If I say, what position is the minute hand at 37 minutes? Well, you're just going to say, yeah, it's at 37 minutes. Now, d1. d1, well, what is the ratio? Or not ratio, rate. You're taking 60 minutes, but it's not over the whole clock of 60. It's only a small segment, in this case 5. And I just realized I did my ratio up wrong way, but it's going to be 5 over 60, right? Because you're only going 5 minutes, like the hour only goes from 12 to 1. So therefore, d1 is just equal to t over 12. So you have the same t, but you have different d's. So that just gives you t minus, plugging in gives you t minus t over 12. It's equal to 20. So 11 over 12 t is equal to 20. So 12 times 20 over 11 is equal to t. Now that's cool because that's our first one. That's equal to a over b. Now, the second one, the second case, I'm going to draw another clock. And I'm going to ask you another question, right? So you start off at 11, right? Your clock starts off at 11. This is 11 p.m. Your clock looks like this. Now, where do you move from this, right? Now, you might say, like, okay, well, it would be like something like this. I don't know, like, no, it would be something like this where it works out. And yeah, like, would you say that one of the minute hands is 20 minutes past the other hand? No, you would not. Like, or, well, you would, but, like, that's not the answer. The reason it's not the answer is because, think of it this way, right? Read the problem carefully. The question says, the last time. So it's actually, I'm just going to like make it like this. Again, it's actually going to be like something like this. It's going to be flipped. And try to think of how that works in your head, but it's just going to be flipped, right? So is it 20 minutes ahead at this point? No. It's going to be the complement of 20, which is just 60 minus 20, so it's going to be 40. So this time, d2 minus d1 will be 40, because I'm going 40 minutes past the d1, because it still makes like the same 2/3, 1/3 ratio, but it's just like flipped or mirrored. So, yeah. Now, d1, or what did I say? d1 was your hour, so d1 is this, d1 is 2. Or d2 is this one. So d1 is just equal to t over 5, or no, t over 12, and d2 is equal to t, right? No, there's something you're missing. You're missing, because at the first, at 12 p.m., or 12 a.m., the clocks started off at the same position. But now at 11 p.m., they're starting off at different positions. So now we need like a little shift, right? Best way to think about it, this is technically 5 minutes ahead of the other clock. So this is t plus 5. And that'll help you because, yeah, like it's just 5 minutes ahead. So d2 is just 5 minutes ahead of the other one. Alternatively, we could do d2 minus, or we could do d1 minus 5. You'll see that that works out to be the same thing. As long as you say that d2 is ahead of d1 by 5, it'll work out. So now we have t plus 5 minus t over 12 is equal to 40. So 35 is equal to 11 over 12t. So t is equal to 35 times 12 over 11. Now we found m over n. And now that's pretty much the problem, right? It was kind of a lot of like logical assumptions, but that's pretty much math in general. So a plus b plus m plus n, that's just 12 times 20 plus 11 plus 35 times 12 plus 11. Now I'm just gonna try making this faster, right? I'm not gonna like try adding it. You have 2 11, so 2 times 11 plus, I can factor out a 12 from that. So this is kind of just me making, like, taking shortcuts in the arithmetic. You'll see that these two are the exact same thing. You could literally just compute this and add it. It doesn't matter. But this is just me being, like, different. Because this is just 12 times 55. And then I guess you could kind of do some more math. But 12 times, I'm just going to use a calculator at this point because I kind of don't want to do the arithmetic. That should just give you 682, which is your answer. So yeah, really nice problem. The only thing I wish it kind of like said, instead of saying tangent, because tangent confused a lot of people. I know when I first saw the problem, I was like, well, dude, what the heck? How can you have a clock that's like this, right? I thought that was what we meant by tangent. I really hope that I really wish that it wasn't like that, because it would have been a really nice problem. But it's fine. Like, the solution is what matters in the end of the day, right? So, okay. Whew. Alright. Last problem. This one is a hard one. So, yeah. There's a good chance if I make a mistake, I'm hoping I don't make this mistake in between it. But if there is, I might cut it out to this point. So, yeah. I guess if you see a cut in the video, you know it happened. But, yeah. Alright. Last one. Alright. So, I'm going to... Okay, so first of all, like, the problem is pretty easy to understand. Now, figure 2, like, is really easy to figure out. Like, figure 2, you should pretty much, like, compared to figure 1, like, I genuinely struggled on figure 1. Like, I took a while to figure that out. Figure 2, it's like, I'm going to save it till the end, kind of like a dessert. Like, I'm going to do figure 1 first, because figure 2 will feel a lot better to do. But, yeah. Alright. So, I'm going to also change color so you can see this. Alright, so first thing, I'm just going to kind of go over this, like, idea. First thing is, draw, like, when you're stuck, draw lines, right? I'm going to draw a line here to here. And then here to here, right? Now, what do I do with these lines? Okay, well, can I figure something out? This looks like a square. Like, I know I drew it bad, but what happens if it is a square? So let's try to prove it. Is it a square? Well, this is 90 degrees because it's a right angle. But wait a second. Any point from the center of the circle to the tangent is 90 degrees, right? That's just a geometry theorem. So this is 90, and by symmetry, this is also 90. Now, when you have a 4-sided shape and 3 of them are right angles, that other one's also a right angle, right? That's just proofs. So, because of that, we have r as this length. Say that's r is our radius of the circle. This is also r. That's cool. That's one part of the problem. And I'm also going to draw this r on the inside of the square. Now what? Well, this is equal to 10 minus r, right? And now I'm stuck. Now I'm like, okay, what do I do? But wait a minute. What happens if I draw this extra line? This is also 10 minus r, right? And this is kind of annoying, but at the same time, this is r. This, like why is this r? Because it's a length from the center of the circle to the point of the end. And is this a right triangle? Yeah, it is. You have a right angle right here. But can I use Pythagorean theorem? No, because you're missing a side length. You don't know what this side length is, right? But here's the trick. You don't need to know it, because this is 90 degrees, and because of these two are equal, and since they're equal and they add up to 90, so therefore they're both 45. So this is just another 45, 45, 90 triangle in disguise, which means that 10 minus r is root 2, or 10 minus r times root 2 is equal to r. Now, I made a lot of logical leaps in that 1 minute, but it's kind of just like you gotta just play around with it. Like, I'm not gonna lie, it took me a long time to see this, and I'm not gonna lie, I also needed some hints, right? I asked in, like, a public Discord server, like, hey, like, I'm kind of stuck on where to start. But yeah, that's, like, pretty much, like, where you get to this. Once you get to this, it's a lot easier to do, because now you just solve for r. So, root 200 minus r root 2 is equal to r. So r plus r root 2 is equal to root 200. Factoring that out, you get this. And then, okay, a lot of work, and we got an r, right? You made a lot of logical assumption. Oh, by the way, I forgot to mention how we got that root 2. That's just another 45. That's just a special right triangle. I'm assuming you have them known. If you don't, it's fine. Remember that if you have x in an isosceles right triangle, this is x root 2. That's just like a trick that's going to help you a lot. And it's like the crutch of any geometry problem, knowing those special right triangles. But anyways, moving on. So you have that r, right? So that is the unshaded area, right? Or we need to find the unshaded area. So that's just 10 squared minus pi r squared. Where did I get the 10 squared? That's just the shape of the square, right? So it's just everything in the circle. Oh, and times 1 over 2 because it's a semicircle. Okay. I think we have everything we need. So 100 minus pi, or pi over 2 times 200 over 1 plus root 2 squared is equal to m1. I'll just go ahead and simplify m1 for you. So yeah, I'm just going to get to that. Times 200. What is 1 plus root 2 squared? You could FOIL it out. Also remember that if you have a plus b squared, that's just equal to a squared plus 2ab plus b squared. That's just another thing you might want to remember. So yeah, all right. 1 plus 2 root 2 plus 2, right? So that's just 3 plus 2 root 2. All right. And I have everything I need. Is there any more simple that I can do? Yeah, I got 100 minus 200 pi over 6 plus 4 root 2. Okay, I don't think I can simplify that anymore. All right, that's equal to m1. All right, is there another color I can do for the other one? Yeah, that's pretty, like, okay. Now, I'm going to make a copy of this. Okay, this one is a lot easier to do than compared to the first one. The first one, you have to make a lot of geometry, like, leaps. But this one, I feel like is a lot more easy to do. So you have 10, right? The radius is literally just equal to 10, right? R is equal to 10. The area is just r squared pi over 4. That's the area of this quarter circle. So you just have 10 squared pi over 4, which just equates to, yeah, I don't know how it took me a second to figure that out, but 25 pi, right? 100 over 4 is just 25. Now, that's just 100 minus 25 pi is equal to m2. Now, I have m2, I have m1. Now time to do the math. Okay, so you need to find m1 minus m2. It's the positive area. In other words, which of the, like, let's subtract them in the right order. Figure 2 is bigger than figure 1. So let's just do 100 minus 25 pi minus whatever the other one is. Yeah, a lot scarier looking, but yeah. Why is it not working? I don't like how it's like. I guess I'll just move this over. Alright. Yeah, cool. Okay, that's equal to the sum of the differences. You'll notice that this cancels out with this. So negative 25 pi plus 200 pi over 6 plus 4 root 2. Alright. Now, that is equal to, so I can factor something out. Yeah, I can factor the 25 pi out. So 25 pi over negative 1, or yeah, factor out negative 1 plus 8 over 6 plus 4 root 2 right? And what do I even need to get in the form of? Like, what am I looking for? A root B, yeah, looks pretty right. So I guess we'll just keep factoring until we get something. So yeah, I'm going to handle that 8 plus 6 plus 4 root 2 by itself. That is just going to be 4 over 3 plus 2 root 2. That's just me dividing by 2 on the top, like canceling out that 2. That's because you have 2 times 4. And you can factor out that 2 as 3 plus 2 root 2. So you'll see that's how like the 2's cancel out. And now, I actually don't remember if they teach rationalization in 8th grade. I remember they did for my brother, because my brother took geometry when he not during COVID, like my older brother, but I know mine was during COVID, so the whole curriculum was whack. It doesn't matter. Like, if you don't know how to do it, well, I'm gonna explain how to do it, right? To cancel out this radical in the bottom, you just do the conjugate, which is just the same thing, but you put a minus in the middle, right? The reason this works is because of our good friend difference of squares. So yeah, you'll see that this just becomes 4 times 3 minus 2 root 2 over, you can flow it out. I'm not, because there's a really nice shortcut to this, which is just 9 minus 8. So this should just equal to 12 minus 8 root 2. And then the bottom is 1. All right, we're nearly there. So now we have 25 pi times negative 1 plus 12 minus 8 root 2. Wait, did I lose a negative or something? I hope I didn't. Okay. Wait, what was the form I was supposed to get it in? Okay. Okay. This is funny. Alright, I just realized I made a crucial mistake. This is like at the end of the problem. I'm probably just gonna figure out if I can just add a cut or something. But at the very end, I realized I made a really big mistake. It's not a big mistake. Like, I'm happy I caught on to it. Basically, how I remember how I factored out this negative 25. That's huge. That has huge implications, because of that, there's a negative 25 that I factored out, meaning that I never accounted for that negative 25, right? It should be like this. However, yeah, it was pretty much the right problem. It was just a really small mistake. So, yeah. Alright, so yeah. Basically, I got the negative 25. All the other math is right, but I factored out the negative 25, and the original solution has a positive 25. So we redistribute the negative just to account for that. So it's actually 8 root 2 minus 11. So yeah, I know probably early in the video I said maybe it wanted you to like that. No, that was just me being silly, and I forgot that I factored in negative 25. Really small mistake. All the other math logic is the same. But yeah, this video is 53 minutes long, so I was bound to make a mistake like that somewhere. Really unfortunate that it happened at the end, but I'm not going to re-record. Like, yeah, like, sorry. Okay, so 8 root 2 minus 11, that's how it looks like. So 8 plus 2 plus 11 squared is equal to 21 squared, which is just your final answer of 441. So long problem. But yeah, I know you said your geometry teacher got half of it. I'm not gonna lie, she probably got this blue half. Like, not like the bottom, like this, like, because this part is pretty trivial, right? Like, that's why I said let's save it to the end, because it's so short. This one you have to do a lot of geometric thinking, and it's really thinking outside the box. It's hard thinking outside the box, but nevertheless, it's thinking outside the box. So yeah, that's a lot of, it's problem 14. So yeah, like, I hope you had fun with these problems. But yeah, thank you for asking the solutions. Not a lot of people actually really care to see the solutions to their mistakes, and I feel like it's a really undermined aspect of math team. So yeah, that's pretty much it.